In the riboflavin experiment, our purpose is to determine the concentration of an unknown riboflavin solution. So we know what it is, but not its concentration. And that is what we will find through several determinations, calculations, and so on. Riboflavin, otherwise known as vitamin B, is common in foods and in biological redox reactions. Riboflavin has a yellow color. What that means is it absorbs light other than yellow. Where it primarily absorbs is in the violet region. The absorbance spectrum of red food color is shown here. The absorbance spectrum is absorbance on the y-axis versus wavelength on the x-axis. And we see for red food color that it primarily absorbs in the green region. The absorbance spectrum for riboflavin looks rather similar to this absorbance spectrum, except it is shifted much to the left. That is, the peak is between 400 and 500 nanometers. So we will be working with a spectrometer. Let me show you the diagram for the spectrometer. It is here. It's rather large. It's about 1.5 feet in length, and it sits on a lab bench, and we put our sample into what's called here the sample compartment. So we open up the little door, we put our cuvette in, which is really just a test tube that fits the spectrometer. We set the spectrometer to a certain region of light that's being sent through it. In this example, the digital readout shows 400 nanometers, so that's the wavelength of the light being sent through the sample. And the absorbance shows up in the display. We have to do some zeroing and things like that. You can see to zero, we have to zero transmittance, we zero the absorbance. We adjust the wavelength with that dial called wavelength adjustment. And when we're all set, we see the wavelength in the display. So you will see in the experiment video, you will see the spectrometer shown in the video. Alrighty, so that's how we measure absorbance. And absorbance is an equation which is equal to negative log of I over I naught. Now, what is everything here? So at a given wavelength, we have a certain intensity called I naught going in. The instrument knows how much intensity, what is I naught. It then goes and interacts with the sample shown here in this test tube. If light is absorbed, then the intensity I of the light coming out is less than the intensity I naught. And that will be then transmitted to absorbance via that equation 1. Absorbance is also equal to some terms, the epsilon, the molar absorptivity, times L, the length of the test tube, the diameter of the test tube, times C, the concentration. Concentration is ultimately the one we want. So absorbance is equal to a constant, that would be this epsilon times L times C. So we are going to be measuring absorbance. We will then be determining a way to translate from absorbance to concentration, since ultimately we want to determine the concentration of an unknown riboflavin solution. Now, we will be working at the wavelength that is called the analytical wavelength. So going back to this red food color absorbance spectrum, where the absorbance peaks in this green region, the peak of it has a certain wavelength associated with it. That's around 525 nanometers or so. That's called the analytical wavelength. That's where we get the most accurate results. So what we need to do with riboflavin is measure the absorbance at wavelengths all the way from 400 to 500 nanometers, because that's where it absorbs. We will be doing that every 10 nanometers so that we generate an absorbance spectrum. Where that peaks, which is at around 450 nanometers, is then where we will determine the absorbance of our unknown. Now, how we're going to go from absorbance to concentration. We're going to do that by generating a calibration curve, which is a graph of absorbance on the y-axis versus concentration on the x-axis. We see here in figure 3 the calibration graph for a material called fluorescein, and we're going to generate a rather similar one for riboflavin. Now, in order to have absorbance at different concentrations, what we will do is be given a stock solution whose concentration we will know. Stock solution, that means it comes from the stock room, and we are going to take that stock solution and make several different dilutions. Those dilutions are given in table 3. In cuvette or test tube 1, we're going to take 2 mLs of, actually it's 2.00 mLs of the stock solution and put it in a test tube called cuvette 1, and we're going to, actually no, we will put it in this volumetric flask. So we will measure 2 mLs of the stock solution, we will put it into the volumetric flask shown in figure 5. Then with distilled water, we will fill our flask to the 10 ml line. So we're taking 2 mLs, diluting it to 10 mLs. That will give us our most diluted solution. We will then pour from our volumetric flask into cuvette 1. Then we will make the second concentration solution. That will be 4 mLs of our stock solution. Put into our volumetric flask, we will dilute it to 10 mLs. Then pour that in cuvette 2. Then we will do the same with 6 mLs, pour that into cuvette 3. 8 mLs, pour that into cuvette 4. In cuvette 5, we have the straight stock solution. I will give you the concentration of the stock solution. You will find that in the experiment video. So we will have these 5 different concentrations, and we will then, in our spectrometer, measure the absorbance of each dilution. Now, we will have to determine the concentration of each solution. So we do that using the equation M1 V1 equals M2 V2. That's our dilution equation. Where in our dilution equation, M1 is the stock concentration, V1 is the volume, 2 mLs or 4 mLs or 6 mLs or 8 mLs or 10 mLs. M2 is our concentration that we're after, and V2, for all of them, we diluted to 10 mLs. So V2 is 10 mLs. So from M1, the stock concentration I give you in the experiment video, times V1, which would be either 2 or 4 or 6 or 8 or 10, that's equal to M2, our concentration unknown, the one that we're after for this calibration data, times V2, always 10 mLs. So all of those mLs have 0.00 after them. Alrighty, so that will allow us to determine concentrations, and we will have absorbances. So then we will make a graph on Logger Pro, and I will show you that graph. It will be available in Canvas. It will be absorbance versus concentration. That's our calibration curve. And we will then notice the data is linear. We will fit that to a linear function. We will have a slope and a y-intercept. And what we then have is an equation, absorbance A equals our experimental slope, you'll see that on the graph, times the concentration C, plus the y-intercept, which again is on the graph. Now, we will have a full equation, A equals slope times C plus y-intercept. So we'll have a number for slope and y-intercept. So we will have absorbance as a function of concentration. We'll have the equation. Then what we will do is measure the absorbance of our unknown. And we will then, with that absorbance, use our equation. We will put our absorbance of our unknown into our equation for A, the absorbance. We have the slope, we have the y-intercept. Our only unknown in that equation will be the concentration of our unknown, which is what we are after for this experiment. Alrighty, so part A of this experiment is generating that absorbance curve, determining the peak wavelength, the analytical wavelength. Part B is to make those dilutions, and part C is to determine the absorbances of those different concentrations. And then in the last part, we go to the computer and use Logger Pro to make an absorbance graph from our data of part A and make then the calibration curve from our part C information. All right, so read through the experimental procedure so that you understand what's going on as I do the experiment and you watch it on the experiment video. And here are the instructions that we will work with on the Logger Pro. For our two graphs, graph 1 is this absorbance versus wavelength graph, the absorbance spectrum graph. Graph 2 is the calibration graph, the absorbance versus concentration. Alrighty, so as usual, you can skip the pre-lab. And then for the report, on the graph, you should be able to read the absorbances at the different wavelengths. I will also probably tell them to you in the video. The analytical wavelength, well, that's where we have the maximum absorbance. And then parts B and C, we have the dilutions. I will give you the riboflavin stock solution molarity in the experiment video. Unknown letter, okay, I'll give you that as well, or maybe I'll forget, but it won't matter. And we will have then those 5 dilutions, cuvettes 1 through 5, and the volume of the stock solution, you know from table 3 for cuvette 1 is 2.00 mLs, cuvette 2, 4.00 mLs, cuvette 3, 6.00 mLs, cuvette 4, 8.00 mLs. Cuvette 5 is the straight stock solution. The final volume for the cuvettes is always 10.00 mLs. So from the V1, volume of the stock solution, V2, the final volume, you will calculate the final solution concentration using, as we talked about earlier, M1, that's the stock solution molarity, times V1, the volume of the stock solution for the given cuvette, and you will divide that by the final volume, which is 10 mLs, always 10.00 mLs. That will give you the final solution concentration that you need for each cuvette. Where cuvette 5, it is the stock solution molarity. The absorbances you will find in the experiment video. And then we have unknown 6, which we have, of course, not diluted. We're after its concentration. And the absorbance of it you will be given in the experiment video. Okay, then we have the calibration graph, which has the slope that's, I will probably tell you in the experiment video, and you'll be able to see it on the graph. I'll give you the y-intercept, also on the graph, and the correlation coefficient. Okay, so using your slope and intercept, write the equation for the best fit line on the calibration curve. So that means A equals slope C plus y-intercept using the data of the slope, the y-intercept. And then number 5 is using the interpolate function on the calibration graph. What is the concentration of riboflavin in the unknown solution? Change that to using your equation from step 4, what is the concentration of riboflavin in the unknown solution? So back up here, you have the absorbance of your unknown. That's cuvette 6. You have its absorbance. Here in step 4, you have an equation, A equals number, C plus number. You put the absorbance in there, you do some algebra using your slope, your y-intercept, do the math correctly. The concentration, C, is your only unknown, and that is the concentration that we want. There are a few questions here, and once you're done with those, then you are done with the report. Make sure you're happy with your answers, scan it as a PDF file, and submit it.